has quite yet lived up to its reputation of winter. Not yet quite started. I think reasons are not so difficult to guess. We had thermal field theory going on for the last 9 days, and that we have Gluon plasma from today. I don't think winter is going to set in time soon before, say, the first week of December, until the circle gets over. So anyway, it's good. So far, winter has not quite yet set in. This is good for us. So today we are starting our second series of lectures on Gluon plasma and black hole physics. In the morning we will have Gluon plasma lecture series. I'm very delighted to invite Professor Rajeev Bhalerao, Professor Somen Datta, and Professor Bidangu Das. All of them are distinguished physicists in their respective area and well known not just in India but across the globe. So we are very happy that they accepted our invitation and took time out of their busy schedule to come to this desert town, which is far from everywhere. I'd like to briefly give the bio of Professor Bhalerao. So Professor Bhalerao did his pre-PhD education from University of Pune and IIT Mumbai, and then he did his PhD from IIT Kanpur. Thereafter he held several academic positions in IIT Kanpur, Brooklyn College SUNY, fellow at Weizmann Institute, Rehoboth, and then Los Alamos, visiting professor at McMaster, and several long and short-term visiting positions across the globe. Actually, Australia, Canada, US, France. He has been at TIFR since 1984. His research interests are in the areas of ultra-relativistic heavy ion collisions, space-time evolution of Gluon plasma, fluctuating initial conditions, collective flow of QCD matter, relativistic impact. Signatures of QGP and QCD phase diagram. We also have with us Professor Somen Datta. He's a professor at the Department of Theoretical Physics, TIFR, and he had his undergraduate education and postgraduate education from University of Calcutta. Did his PhD from TIFR with Professor Raju Gawai, and has spent many years at Bielefeld before he joined TIFR in 2006. He works in the area of QGP, in particular the non-perturbative regime, using Monte Carlo techniques, studying the hadrons with heavy quarks that may hold the key to our understanding of matter-antimatter asymmetry in the universe. Professor Bidangu Das Mohanty is not yet here, but all of you may be aware that he is the recent recipient of the Bhatnagar Award. We are very glad that he has found some time from his busy schedule and is going to be the tutor for this course. He is currently, he wrote to us that he will not be able to join today. In fact, he was being felicitated today by the government of Orissa, by the governor. So he will probably be here by tomorrow. So he is presently professor at the National Institute of Science, Education and Research, NISER, Bhubaneswar, and he did his education, pre-PhD education from Utkal University, PhD from IOP Bhubaneswar, and was a postdoctoral fellow at Lawrence Berkeley National Laboratory, and works in the experimental high energy physics. So this is quite interesting that we have an experimental high energy physicist who's going to give you tutorials for PhD school that speaks for the breadth of his understanding of both experiments and theory. And he works in QCD phase diagrams and transport properties of QCD matter and various signatures of Gluon plasma. We have a very distinguished speakers in this series, and I do hope that you all enjoy the lectures. Please do turn in time and make the most of this opportunity that you have got. Over to Professor Bhalerao.
Can you hear me? I'm sorry for this hiccup here at the beginning. So let's begin. Let me thank the organizers for inviting me here and giving me an opportunity to interact with all of you. How many of you are here? I assume everybody is working in theory. I'm not my list here. And how many of you are working or planning to work in this area? fraction of you are actually trying to work in this. But even for other people, I am going to discuss topics which will be of use to you, even if you are not trying to work in this area, like some basic ideas of relativistic thermodynamics, relativistic kinetic or transport theory, relativistic fluid dynamics. So these are some of the topics which will be useful even if you are working on string theory, for example. So I will keep that in mind, that you may or may not work in this area. It's always good to have a broader base of knowledge. Okay, so this is the hot stuff today, and this is an experimentally driven field. So we have one experimental tutor, other theory tutor. And the progress is very rapid because the experimental program is also ongoing for us 10 years or even more. So point is, this is closely related to experiments. Okay, so this is some outline. Is there a pointer? A stick? So I am going to first introduce this field of alpha relativistic heavy. A stands for nucleus, nucleus collision. A is the atomic number, or how many nucleons are there in the nucleus. That's symbol A. Then I will talk about how this QGP or quark gluon plasma was discovered in the lab about 10 years ago. So discovery of the hottest, smallest and the most perfect. So I will explain each of these words. Why the hottest? The temperatures that we are talking about are 10 raised to 12 degree Kelvin.
I think that should be
Okay, so this is for non-experts. This field is an interface of particle physics and high energy nuclear physics. It's a very multidisciplinary field, and it draws heavily from many areas, in particular from QCD, perturbative QCD, non-perturbative QCD, or classical, semi-classical QCD. It has overlaps with thermal field theory, relativistic fluid dynamics, relativistic kinetic or transport theory, quantum collision theory, apart from the standard statistical mechanics and thermodynamics. QGP at very high temperatures and vanishing NB. NB stands for the net baryon number density. You have many body systems with equal number of baryons and antibaryons. The net baryon number is 0. So NB will be 0 in that case. Even if the density may be very high, but the net baryon number density can be 0. So we are going to talk about, suppose that its temperature is high and NB is very small, then that is of cosmological interest, because early universe was in such a state. Temperature was high and the NB was very low, equal number of baryons and antibaryons. On the other hand, quark gluon plasma at low temperature, low means relatively low, and large NB, it is of astrophysical interest because neutron stars, for example, are relatively low temperatures, but NB is very large. Net baryons in the neutron star is very large. And finally, because of this connection between black hole physics and fluid dynamics, or gauge gravity duality, even string theorists I got interested in this field. So it touches many areas of physics. And as with high energy or physics students know, the science of the small, that is elementary particle physics, is deeply intertwined with the science of the large, that is cosmology, the study of the origin and evolution of the universe. There are a lot of similarities between So the Big Bang and the Little Bang. Big Bang, you know, by Little Bang I mean the collision of two ultra-relativistic big nuclei like lead on lead or uranium on uranium, gold on gold. That has been called a Little Bang. You will know why. So a lot of similarities between these two. So what you see here is the temperature history of the universe. Temperature in degrees Kelvin plotted as a function of time after the Big Bang in seconds. On the extreme left top corner, the Big Bang happened earlier than that. And at very early times or very high temperature, temperatures greater than 10 raised to 12 degrees Kelvin, the universe was in the state of Quark Gluon plasma. There were quarks, anti-quarks, gluons. There were no nuclei, forget about atoms, but not even protons, neutrons, or nuclei. And as the universe expanded and cooled, at some point, when the time was roughly a few microseconds after the Big Bang, the universe underwent a transition, QCD transition. There were other transitions earlier. Electroweak transition happened much earlier, but hadronization transition took place at those coordinates, which you see the temperature roughly few microseconds. Further on, as the temperature cooled further, the nucleosynthesis happened. The nuclei were formed. First the protons, neutrons, and then the nuclei. Some of you may have heard about this book by Steven Weinberg, The First 3 Minutes. 3 minutes is 180 seconds. So 180 seconds would be somewhere here. This is 1, this is 1000, so 180 would be somewhere here. So that's when the nuclei were formed. So that was the era of radiation dominating era. Later on, much later, atoms were formed, and then we go into the matter-dominated region. Universe, of course, on a much smaller length and time scale. The Gluon plasma that is formed lasts only for about 10 raised to minus 24 seconds, and the size is roughly 10 femtometer per inch. So before we talk about QCD phase diagram, this is the phase diagram which all of you have seen, phase diagram of water. What is called is pressure as a function of temperature.
So when we are the temperature that we are creating a rate, so how does it compare with after how many seconds of the age of the universe?
No, we are here, right?
No,
so,
yeah. I'm saying that the temperature that we have reached in rate.
Yes.
So that corresponds to the temperature of the universe at what age?
Temperature that we have reached are higher than 10 raised to 12, of the order of 10 raised to 12 degree Kelvin. So we reach this region. Yeah. But of course it lasts very short time. Yes, 10 raised to minus. So this is the phase diagram of water. Pressure in atmospheres plotted as a function of temperature in degrees Celsius. Is 10 raised to minus 3, 1, 217, etc. And these are the well-known 3 regions: solid water, liquid water, and gas or vapor. These are the phase transition lines, and this is the famous triple point at which all 3 phases coexist. That is solid, liquid, gas, they all coexist. The temperature is slightly higher than 0, 0.0098, and pressure is very low, 10 raised to minus 3 atmosphere. Now, everything is known with fairly good accuracy. All these points, look at this, 6 into 10 raised to minus 3, 217.7. So 4 significant places we know. This is, of course, the boiling point. The water changes into vapor. This is the freezing point. Water changes into ice. And in interestingly, this line, the first order phase transition line, ends here in the critical point. So if you cross this line anywhere below this, there is a first order phase transition. There is a distinct difference between liquid water and the gaseous water. There is a phase transition. However, if you are here above this point, then there is no sharp distinction between two phases. You can go from one phase to another smoothly without encountering any phase transition or discontinuous certain phase transition. It's a smooth, what is called smooth crossover. There is no distinction between the two phases. It's called a supercritical fluid. And we know the coordinates of that point fairly accurately. So the important thing I want you to remember is this is very well known. And what is the underlying interaction here between the molecules? Electromagnetic, of course. Now you can ask a similar question. What would be the phase diagram of matter if the underlying interaction is not electromagnetic but strong? So the constituents of the matter, if they interact strongly, what would be the phase diagram? So that is what is called QCD phase diagram. But unlike here, not enough is known about the QCD phase diagram. This is the schematic diagram. The coordinates brightness is not very good. Not helping. So unlike the water phase diagram, this is schematic. And we know this, okay, what is plotted is temperature as a function of the net baryon chemical potential. The chemical potential and density are related. So mu B is related to NB, the net baryon number density and or the net baryon chemical potential are related. So sometimes this is used, sometimes the density is used. And this is the zero temperature and zero net baryon density. This is where this is vacuum state. So on this scale, most of the condensed matter physics collapses to study of this point here. And this is the region. You see two or three broad regions. One is this region called hadron gas. That is the low temperature and low density region, and that's where we live. We have low temperatures and densities are low. This is the phase of hadron gas. Now on this here, where temperatures and density is high, is the phase of Quark Gluon plasma. And here, when temperatures are relatively low but densities are very high, is the neutron stars exist here. And this is the hypothetical phase called color superconductor. It's not yet seen in the lab. Even neutron stars are very difficult to study in the lab. It's hard to create such high densities and at low temperatures. You can create high densities or energy densities, but the temperature also goes high. So it is difficult to create this part of the phase diagram in the lab. But one can make some models. You have observations of neutron star, astrophysical observations. You can draw some conclusions. Neutron stars are real, but we don't know where exactly they lie. That's why there is this double-headed arrow shown here. This is hypothetical. It's not seen. Now, why is it predicted? The reason is the following. You know ordinary superconductors, where what is the interaction? The interaction between electrons, which is we know to be repulsive. Electrons repel each other, but still they form, under certain conditions, they form a super pair, which is the bound state of two electrons. How does it happen? It happens because of the phonons. The two electrons interact via phonons, and that overcomes the repulsive interaction. But since this is a very delicate phenomenon, it doesn't last if you increase the temperature. Ordinary superconductivity gets destroyed at high enough temperature. Now here, unlike two electrons forming a pair, two quarks form a pair. And it is known that in certain channels, sometimes it's not working. Under certain channels, that is for certain spin, flavor, color, degrees of freedom, there is an attractive interaction between quarks. So, and because of that, this is a very robust phenomenon. Color superconductivity is supposed to be very robust. The gap, superconductivity gap, is much larger. Anyway, so we are not going to talk much about this. Okay, ordinary nuclear matter, that is here, temperatures are negligible, densities are less than that of neutron star. To form a neutron star, you need densities which are 4 to 5 times the ordinary nuclear matter density. Okay, now there is supposed to be a phase transition here, phase transition line. But before that, let's talk about this axis, the temperature axis, when the NB is 0. Now this is the region, and 0 NB or close to this axis is the region which can be studied from first principles using Lattice QCD. Soman is an expert in Lattice QCD. So Lattice QCD is applicable at low NB, 0 NB or low NB, near this temperature axis. And we now know, after several years of Lattice QCD study, that this transition occurs here. It's not a phase transition. Again, it's the smooth crossover. You can go from QGP to heteron gas without any phase transition. But very often one says it is QCD phase transition. But it is actually a smooth crossover. There is no thermodynamic phase transition. And that occurs at temperatures which is roughly 155 MeV. So 1 MeV is approximately 10 raised to 10 degrees Kelvin. So 155 would be of the order of 10 raised to 12 degrees Kelvin. That's where this smooth crossover occurs. And this is an expectation from various ideas that there is a first order phase transition. Now if there is a smooth crossover here, then this line has to end somewhere. And that is the critical point which you saw even in the previous phase diagram. The first order phase transition line ends here. It's supposed to end here. Now this is again a expectation. It has not been seen in the lab, and it would be a great if we actually see it in the lab and we can fix this coordinate. We only know its position roughly from theoretical ideas, but we do not know the exact coordinates, unlike in the previous phase diagram. Now what you see are these lines, they refer to various experiments. When you hit two nuclei on each other at very high energies, then you end up somewhere here in Quark-Gluon plasma phase. See, this is a phase diagram. That means every point here represents a thermodynamic system in equilibrium. If the system is not in equilibrium, we cannot show it here. So when two nuclei collide, whatever happens is not always in thermodynamic equilibrium. So those points we cannot show here. But at some point, if it reaches equilibrium, then you can start from there. And later on, as the system expands and cools, again it goes out of equilibrium. So you cannot show it here. That is why these lines are of finite lengths. This is where the collision happens. So the line starts here and it ends somewhere below this. So these lines represent the evolution of the system at different initial conditions. These are relatively low energies. These are, as we increase energies, as we approach it. These are the experiments done at RIC, Brookhaven National Lab, and these are the LHC experiments which are ongoing. Everything is, even RIC is ongoing program. So RIC and LHC. In the early universe is here. Early universe underwent this kind of evolution. The LHC experiments see this region, weak experiment series, and there are plans or there are programs to study even lower. Yeah.
How do you know on the experiment that QGP is melting form?
I'm going to explain that later in the talk. What is explicit evidence for the formation of QGP? So I think I have explained most of the things in this diagram.
Sir, he said that microphone volume will have to increase.
Schematic. So before we proceed, I have to define QGP. What is meant by QGP? So this is our working definition. This is defined as locally thermally equilibrated. I will first read it and then explain. Locally thermally equilibrated state of matter in which quarks and gluons are deconfined from hadrons so that they propagate over nuclear rather than merely nucleonic volumes. Now let's try to understand this definition. You know that quarks and gluons are normally confined inside protons. So this is the state where they are not confined. But their deconfinement over what scale? Nucleon size is, we know the size of nucleon? Fermis? 10 raised to minus 4 Fermi. One radius of a proton is roughly 1 Fermi. Roughly 10 raised to minus 13 centimeters. And that is the size of the proton. What is the size of the nucleus? How many Fermis? If nucleon is 1 Fermi, let's say lead nucleus which has 208 nucleons, what is the size of that roughly? 100,000 times the proton size. And I'm not talking about volume, I'm talking about radius. Atom is roughly of the angstrom size. Nucleus is a few times the proton size. Even the largest nucleus, radius, is just roughly 5 or 6 times the size of the radius of the proton. So the lead nucleus or uranium nucleus, which is some of the heaviest nuclei, the radii are about 6-7 Fermi. Nuclear radius goes like radius of the proton is 1 Fermi. Radius of the nucleus is it goes like cube root of the number of nucleons, so it doesn't increase very rapidly. So when we talk about deconfinement,
where does the 1.12 come from?
Is the fit to the data. And this is the fit to the data. There are of course semi-empirical formulas, but basically these numbers come from fit to the data. So when we talk about that QGP, quarks and gluons are deconfined, that doesn't mean they go all over. They are deconfined over a scale, a length scale, which is much larger than the scale of a proton or a nucleus. Nucleus also, quarks and gluons are confined. So here we are talking about length scales of the order of 10 Fermi. That is 10 times the radius of the proton. So that is the length scale over they can move around. That means they are deconfined over that length scale. And then there is something called local equilibrium. Global equilibrium and a local. What is this sound? No, it's outside.
That is a class.
Okay. So equilibrium can be either local or global. In global equilibrium, the temperature and other thermodynamic quantities are the same everywhere. They are space-time independent. But in a local equilibrium, the temperature and other quantities can be space-time dependent. So there can be situation where you cannot even talk about temperature. System can be in a state in which you cannot even talk about temperature of the system. So that is not an equilibrium state.
So global, say if it is over across the 10 for me.
If you can manage that, out air for example here, the temperature is roughly the same throughout the room, and also of course is also roughly time independent. So the air is roughly in a global equilibrium within this room. So in this case, we will not be able to have a global equilibrium of quark-gluon plasma, but we'll have a local equilibrium.
But when you say global, it is say across the size of formation.
Whatever system you have.
If it is 10 for me,
Yes.
then you expect that it is equilibrium across 10 for me.
If you can achieve that, temperature constant over 10 Fermi and independent of time also, then you would say that QGP is in a global equilibrium. But that is not what actually happens in the experiment.
So does it mean temperature fluctuation is maybe less than the average temperature of the medium?
Of course, in equilibrium there are fluctuations, but apart from that,
In the case of local thermodynamic equilibrium,
there will be fluctuations. Even in global equilibrium there are fluctuations, but if you ignore fluctuations for the time being, temperature is almost space-time independent. But in a local equilibrium that is not the case. The temperature depends on space-time. From point to point it varies. But there are regions in which you can talk about temperatures. Within that small region, the temperature can be taken to be the same. Now you would say that would be the more general situation, but that's not so. There are situations where many body system may not be in equilibrium at all. So then you cannot even talk about temperature there. There is no such thing as temperature if system is not in equilibrium. So local equilibrium is a step ahead. Yes.
So this local is related with the mass and path of the particle. So how much local means what?
Yeah, there are various length scales. We'll talk about it later in the course. But temperature, of course, has to be larger over the length scale of mean-free particle. So this is a deconfined or locally thermally equilibrated state of matter. These quark-gluons are deconfined. Okay, I explain everything. So what are the two essential ingredients? The degrees of freedom between quarks and gluons. In the nucleus, the degrees of freedom are not quarks and gluons. The most convenient degrees of freedom are protons and neutrons, maybe few pions. But here the degrees of freedom are quarks and gluons. That is one requirement. Other requirement is that matter has to have a local thermal equilibrium. So if you want to claim that you have discovered plasma in lab, then you have to show that this has been achieved. You have to show this condition has been fulfilled. Only then you can claim that QGP is formed in the lab. Okay. So the big idea in this field is to map out the QCD phase diagram. I said that what you saw is a schematic diagram, and the big idea is to fill it out quantitatively, map it out quantitatively, and also to test. And if you can do that, if you can see quark-gluon plasma is found, that would support the predictions of QCD. Because Lattice QCD has predicted that quark-gluon plasma should be formed above certain temperatures. And that's just a prediction. You have to actually verify it in the lab. So this is the only way you can do that. The only experimental tool that you have is a collision of two nuclei. There is no other tool for studying quark-gluon plasma in the lab. So the okay, and theoretical tools are, as I said, Lattice QCD. And apart from that, this is first principle calculation. They are very expensive to do it on the computer. It takes a long time. So there are phenomenological models which try to mimic QCD. There are various models. There are also some effective theories. And more recently, the ADS-CFT correspondence also tells you something about these fields. So these are the theoretical tools. Experimental tools are these machines at successively increasing energy densities. SPS is at CERN, a super proton synchrotron. It it was working in 1990, around that time. Now it's no longer in an active mode. RIG at BNL is started around year 2000 and it is still continuing. LHC started a few years ago, and you must be familiar with high energy physics program at LHC. Higgs was discovered, but nucleus collision is also one of the major programs at LHC. There are three major experiments. They call ATLAS, CMS, and ALICE. ALICE is fully our dedicated experiment which studies only nucleus collision, lead. But CMS and ATLAS, although they are basically high energy physics machines, they also study nucleus collision. So all three big programs study nucleus collisions. And these are some upcoming lower energy facilities which work at somewhat lower energy, because we want to study different regions of the phase diagram. So we also need to do experiments at lower energies. That will be achieved by these other machines. So this field has been active for few decades. It will remain active for at least one more decade. So this is what we have learned from Lattice QCD. And these are, what is plotted is epsilon. Epsilon stands for energy density as a function of temperature. And to make it dimensionless, it has been divided by T raised to 4. Energy density goes like temperature raised to 4 dimensionally. And this shows pressure, again in the same units. Pressure is also scaled by T raised to 4 to make it dimensionless. And here it's plotted as a function of temperature. Goes up to approximately 1000 MeV. Okay, let's look at this figure. Temperature is increasing, energy density is increasing as temperature increases, and then it tends to saturate. Same thing is pressure. Now you see here, there is no sudden change in the energy density. There is a rapid change, but not a discontinuous or a abrupt change. So first order phase transition is ruled out by these results. But what you see here is a rapid but smooth increase in these quantities, and that happens around 155 degrees, which I talked about that number when I showed you the QCD phase diagram. And this shows, the inset shows the same region in a greater detail. So 100 to about 250, 155 would be somewhere here. And that is where the smooth crossover occurs. This is again 155. Now you see here, what do you see? What are the major, okay, now there are three different lines, they refer to three different calculations. Successfully more and more accurate in lattice, more fine more accurate. So this is, stands for 6, 8 and 10 points in the time direction. 10 is the most accurate among the three. Now what do you see here? First of all, as I said, there is an increase in these two quantities, but
points in time.
Yeah, there is a time axis and the space axis.
Yeah.
So in the time axis, they have taken 6 different.
So how many sizes you are taking of time axis?
How many points you have in the time axis? Sorry? Capital N. Yes, it's a n sub t. N sub t is the number of points in the time axis, time direction.
But this is loss of precision, so how to define value of the
Yeah. There is something called susceptibility, and you find out where it peaks. That is one way of pointing out that
So we
temperature.
cannot find out the pressure temperature from this one?
Not accurately, because it is, we don't know where here, but there are other variables you plot as a function of temperature, and if there is a peak, then something is, you can identify the location, exact location where the peak occurs. So that there are many variables, so each of them gives slightly different temperature. temperature, but 155 is
What is EOS?
equation of state. Equation of state, the relation between various thermodynamic quantities like pressure, temperature, energy. Okay, so there is an increase. Why is it increasing? Why are these two quantities increasing as a function of temperature? If epsilon and P are increasing, that means the entropy is increasing. The entropy is related to these two quantities. This is a thermodynamic relation. If suppose there is, I am ignoring number densities. This is entropy density, temperature, energy density and pressure. So what you see in this figure is epsilon and P both are increasing. At some in the narrow temperature domain, that means entropy must be increasing. And entropy means disorder is increasing, the number of constituents are increasing. That's what you expect at the confinement, right? If protons and neutrons are broken and quarks and gluons are liberated, each proton has 3 quarks, at least 3 valence quarks. There are many others, C quarks and anti-quark pairs. So when these protons and neutrons are broken, a huge number of degrees of freedom are released. Entropy increases. So that's what you see here. There is, over a small temperature region, they both are increasing. So an increase in entropy of the number of degrees of release of partonic degrees of freedom. Another observation is pressure rises less rapidly than epsilon. That you can look at these numbers on the right hand axis and you can see the pressure rises less than epsilon. Why is that happening? Can you guess? Definition of speed of sound in a system. Speed of sound is square of the speed of sound is dp by d epsilon at keep some quantities constant. Now using this, can you tell me why pressure has to increase slowly, slower than epsilon? Yeah, otherwise it will exceed the speed of light, which we don't want. So that is what is expected. Pressure would rise slowly. Now, high temperature limit, the highest, let's say this is 1000 degrees, 1000 MeV. Even if you go to a temperature as high as this, 1000 MeV would be 10 raised to 13 Kelvin. Even there, this stands for, SB is Stefan Boltzmann, ideal gas. Ideal gas, we know what are the limits of the energy density and pressure. This is about roughly 5 and is roughly 15, so energy density is 3 times. Epsilon is 3 times. In the Stefan Boltzmann limit, energy density is 3 times the pressure. Now, do we find that here? It is roughly 3 times, but it is still away from what you expect. Quantitative values. Roughly 15-20% less than that. That means even at these high limits of temperature, we don't reach the Stefan Boltzmann limit. That means the system that you have formed or that has been studied here on that is not like an ideal gas of quarks and gluons. There are still some interactions left. So this is what has been learned from lattice over the last several years. And these studies have been made at 0 μb or 0 NB, that is on the temperature axis.
So ideal gas you mean should be non-interacting?
Like an ideal gas, this is an ideal gas equation of state.
I mean it should be non-interacting.
Non-interacting. When you talk about ideal gas in a container, it interacts only with the walls and not much among themselves. That's not what is happening here.
Entropy is increasing, periodic carbon has been formed. But when QGP form means that it is like a fluid state, especially like perfect fluid. So in that case, entropy should decrease. Like fluid is order state compared to the gaseous state.
Yeah. So I'm going to show that figure also. Just wait for a few minutes.
Sir, these figures are experimentally observed or
No.
it is calculated?
This is what we learned from Lattice QCD. It's studied on computer,
Okay.
not in the lab.
Okay.
This is a prediction. One would like to check it experimentally. Okay, so yeah. So ultra-relativistic nucleus-nucleus collision. When the two nuclei collide, the whole thing goes through several stages.
Sir, then to reach the Stephen-Boltzmann that situation, so how means what should be the temperature?
We don't know, but it has to be much higher than 1000.
Yeah,
And there are some theoretical expectations that it has to be asymptotically high, only then you will have asymptotic freedom. Temperature has to be extremely high.
Finally, I would ask that, what is it that keeps lattice QCD from going higher than 1000? I mean, are there computational limits which, why should we stop at 1000?
Yeah, why do we stop
For
at?
example, I would expect to go to 2000, 3000, why not?
Yeah, the computer problem, right? This is what
Should be a
called.
computational limit of how much we can.
Comment? Or
Right. So you typically want lattice volume that's still hadronic, that's a few Fermi, and as you go higher and higher in temperature, the lattice cutoff, which is the essentially the upper limit on energy, has to be much larger than temperature. So you have a fixed volume which is few Fermis, and when you go to, let's say, 10,000 MeV, you will have a lattice cutoff. So 10,000 MeV is what? 1/50 Fermi or something. So that's just the temperature, and let's say you want 10 times the temperature as your cutoff, then that's 500, 1/500 Fermi. Okay. So then you want a lattice which has 500 data points in every direction, and that's more than what we can do with current computers. So that's
basically computational capabilities which will put the limit on how high we can go on temperature. Am I right?
That is right. Yes. Yes.
But is there anything to be gained by going higher in temperature?
No, he wants to see
So whether
the
you can
approach to
confirm
the
me that three times epsilon 3 times p, which is the prediction that we need ideal.
But
gas.
really,
what temperature p?
Yeah, but on the other hand, I guess you don't see. You want to do lattice calculations in the regime where you know that perturbative calculations do not work. Once you go to high enough temperatures that things start matching with perturbation theory, you may say, well, now we understand we have perturbation theory to go rest of the way, so you probably don't need to go to 10,000 MeV.
And even if you do calculations here, there is no way you can test in the lab.
Yeah.
In the lab, we have no means to create such high temperatures.
You can match with perturbation.
Temperatures that are created are 100 MeV at the highest technology that we have, certainly. We start somewhere few hundred MeV and then it goes down. So as I said, the whole thing happens over many different stages, and those are listed here. Please ask questions, okay, if something is not clear. So these are a collision of two Lorentz contracted nuclei. We are sitting in the lab, and the two nuclei are coming towards each other at extremely high velocities or energy. So each of them is Lorentz. We feel it. They are all. Both of them are Lorentz contracted. The initial radius of a nucleus, which was some 6-7 Fermi, it gets contracted, and it looks like a thin plate. Two thin plates are approaching each other. Their width is roughly about 1 Fermi because of Lorentz contraction. not arbitrarily small, but it is roughly 1 Quark. So you have two plates coming towards each other and colliding. Then when they actually collide, because of the asymptotic freedom, they tend to pass through each other. We'll discuss that in more detail. They tend to pass through each other, but even then, it's not a fully transparent collision. Large fraction of energy is deposited here, and then rest of the energy is carried away. So that is what is mean deposition of kinetic energy and a formation of a fireball. So that is the next stage. At the instant of a collision, you have a fireball formation. Liberation of partons from these strong chromophils. So in the initial stages, energy is stored in the form of extremely strong color electric and color magnetic fields. And the fields decay by producing quarks and antiquarks pairs. So the energy gets converted from field energy to particle magnetic energy. How do we get asymptotic freedom? See, we are coming with energies. Okay, how much energy I didn't mention so far? Proton mass. Any idea how many MeV or GeV? 1 GeV. Proton mass, rest mass is roughly 1 GeV. More accurate is 939 MeV. So let's say 1 GeV. Now if you boost it, it will acquire energy. So we are talking about energy at Rig machine. The energy of a proton is 100 GeV. That means total energy is roughly 100 GeV, which is 100 times the rest mass. So that much is this gamma factor, 100. So you have 100 MeV proton and another 100, sorry, not MeV, GeV, 100 GeV proton, another 100 GeV proton colliding. Or if we talk about nucleus, each of the protons or neutrons in the nucleus is moving with 1 GeV energy. So if a gold nucleus which has 197 nucleons, then you have 197 GeV coming one way, another 197 GeV coming another way. So roughly 400 GeV, that is your initial starting energy. And some of it gets deposited and some of the remaining just goes away. So the huge energy densities are created, and those energy densities, as I said, are initially in the form of fields, color, electric, magnetic fields. But they get converted into particles. So a huge number of particles are generated. So degrees of freedom becomes huge. At sufficiently high energy, even if at two single protons colliding, you have thousands of particles in the final state.
So my question is that if the lowest contact nuclei comes, and so if the collision happens, when they pass, are they remain same or?
No, they are broken, right? And when they collide, they are not original nuclei.
If that's okay, there may be residue nuclei or baryonic nuclei in the collision area, but when they passes through, and the atomic number remains same or?
It depends on the energy. If the energies are low, then they tend to stop each other. And then most of the baryons are sitting here. But as you increase the energy, then the baryons tend to pass through each other. And at very high energies that we are talking about, very few baryon number at the center is very small. Most of the baryon number flies away. So we have partons, so we have a system, there are many partons, but they are not yet in equilibrium. So you cannot talk about temperatures or pressures because these are thermodynamic quantities. But if you have many body systems and they keep on interacting with each other, keep on colliding with each other with sufficiently high cross sections, then eventually one expects that equilibrium will be reached. Not global, but at least local equilibrium will be reached. then you can start talking about local temperatures. But before that, you cannot even talk about temperature. It is completely out of equilibrium.
Sir, how this deposition of kinetic energy happens actually?
Because they are colliding, right? Two nuclei colliding.
How that deposition is happening?
How means there are interactions. So you can imagine at like one cloud of quarks coming, another cloud of quarks and antiquarks coming, gluons, large number of gluons are coming, and then each of them interact. A huge number of gluon, quark, gluon interactions happening. And as a result of all those parton interactions, energies are deposited there. Many hard scatterings happen at early times.
So what is this fireball? It is something spherical? Or
No, it's not spherical because you have started with two plates. The two plates collide, there is no spherical symmetry. But fireball is just a loose way of describing whatever is formed. But of course, initially there are two plates and so there is a cylindrical symmetry. But eventually when they expand, the whole system expands, it tends to approach more and more like a sphere or a elongated sphere. It's some remnant of cylindrical symmetry. Fireball is just a loose way of it. Okay, so as I said, if they interact enough number of times, then there will be near approximate thermalization will happen. And once that happens, we are
then you can talk about QGP. So the definition of, remember the definition of QGP, local thermal equilibrium.
all that. Next stage, once you have a nearly thermalized system, then you can talk about hydrodynamics. Because hydrodynamics is an effective theory which is applicable when the system is at equilibrium or near equilibrium. So then evolution happens according to hydrodynamics. So that is hydrodynamic expansion. The system cools, it dilutes, densities and temperature go down, size increases, but eventually it becomes dilute.
Enough, then you cannot talk about the system
Even
is
though-
no longer in equilibrium. It is
Too
dilute. It's gone out of equilibrium and you cannot use hydrodynamics there because hydrodynamics is
Not applicable otherwise. But you can use kinetic theory, which is even if the system is not in equilibrium. So then you talk about kinetic theory. Then quarks, antiquarks are still, or hadrons, hadronization has happened. It means hadrons have been formed. Most of them are pions, but they keep on interacting elastically as well as inelastically. So as the expansion continues, at some point there are various abundance, there are many different kinds of particles are formed, pions, kaons, protons, neutrons. But when they do not interact inelastically, then their chemical composition gets frozen. So
that
that
is
is what
called chemical
freeze out. How many
What is the
ratio of
let's say pions to
kaons that gets frozen at that chemical, let's call chemical freeze out. Or there is an analogy in cosmology also. There is a decoupling temperatures for various species, neutrino, photon, etc. So that happens.
so at this time or at this temperature, synthesis without
Yeah, I will talk all that later on. Everything.
has to happen within 10 Fermi.
Time is also measured in
Fermi length is also
measured in Fermi. If you take C to be 1, then time
time is length.
at the same time. Fermis. So within 10 Fermi, whole thing is over. Later on,
Elastic scattering also stopped, and that is after that
their energy momenta don't change anymore. So that is called kinetic freeze out. kinetic decoupling. And finally, you have detectors around the whole system and particles are detected. And what you see in the thousands of particles are detected.
Put it slightly lower. Slightly lower.
Is it okay? And the last stage is you have thousands of particles going away, moving freely like free particles, and then they are detected, all kinds of measurements are made, single particle measurements, multiple particle measurements, and from that you have to deduce whether QGP was formed or not. You have to work backwards. Just like in cosmology, we have cosmic microwave background radiation, and from that you try to go backward and see what was the early living. So a similar idea here also. So it's 5 minutes to 10:30. Shall I continue, or if you want to ask something? Okay, maybe this is the last. So this is just as you have a standard model of particle, you also have a standard model of area and collision. So these are the basic ingredients. Initial stage, I am going to explain how it's handled. It's something called Glauber model, which describes nucleus-nucleus collision starting with nucleon-nucleon collision. There's something called color glass condensate. Yeah, same. So that is one way to describe the initial state. And there is another way, more recent, something called color glass condensate. I am going to talk more about it later on. These are the two popular models of the initial state. Next, the intermediate evolution is handled by relativistic second order hydrodynamics and together with Lattice QCD equation of state. Hydrodynamics is an ideal, a perfect fluid, then Euler's equations are what you use. But Euler's equation only for perfect fluid. If you want to introduce viscosity, then you must have heard about Navier-Stokes equations. But those are called first order equations. There are higher order equations, second order. That is what is state of the art today. Second order hydrodynamics or fluid dynamics is what is used here. And together with Lattice QCD equation of state that I showed you earlier.
What is second about the order?
The ordering is done in the velocity, gradients of velocity. In Navier-Stokes theory, there is viscosity is expressed as the first derivative of velocity. In the second order theories, there are second order derivatives of velocities, expressing the shear or bulk viscosity. Euler's equation has no viscosity, so it's called zeroth order. So this intermediate evolution as per hydrodynamics, and end evolution is again relativistic Boltzmann equation in kinetic theory, leading ultimately to freeze out. And final state, the detailed measurements are available, single particle inclusive, two particle and multi-particle correlation, etc. And aim is to achieve a quantitative understanding of the properties of QGP, that is its thermodynamic as well as transport properties. Properties in equilibrium and properties out of equilibrium. Thermodynamic properties are the properties in equilibrium, but transport coefficients are the properties when the system is not in equilibrium. So one would like to understand all that, because some of it can be predicted from QCD, so you can check. QCD being one of the four basic interactions is important to verify QCD prediction. QCD has been well tested in the perturbative region, but not so in this region, where non-perturbative interactions are impossible. And there are major hurdles in all this program. The initial state is not well defined, not well understood. What should be the initial state just before the collision? We'll talk more about it. Every event is a different event, because you may have a same nucleus coming, lead nucleus, but every time the positions of the nucleons can be different. The time scales are so short that when at the time of collision, locations of the nucleons in one nucleus and locations in the another collision event are not the same, because there is a motion. Nucleons are not static in the nucleus, they are moving around.
But they are quantum particles, so they have some wave function and because if we detect them, then if anyone we interact with them, then wave function will collapse. But if we don't detect it, then wave function will be distributed in whole nucleus sense of all nucleons. So
yeah, there are quantum fluctuations as you said, but the nucleons in the nucleus are not just as electrons are. They are moving, right? In a sense. Similarly, nucleons also, the locations or the probabilities of finding nucleon at one location or other location.
why it will change? Why it will change?
Because you are looking at time scales which are very short, shorter compared to their time scale for motion. The whole collision happens in such a short time that length scales or time scales are much shorter than the time scale that you are talking about. So the locations are frozen. So that's why every collision event is a different event. Although the two nuclei are identical, they are coming along the same line. Because of this event-to-event fluctuation, it is difficult to interpret the data.
Anyway, the debris that comes out of the collision is so varied that event by event fluctuations shouldn't matter much.
Now they do matter. You have to do event by event study. Experimentally, they do distinguish one event from another event, and they record every event separately. So every event has a different distribution. Right. Yeah, because final state will depend on the initial state. The initial state is different. Not only nucleon positions, but the positions of quarks and antiquarks within the nucleon also have quantum fluctuations. So because of all that, every final state is different if you look carefully enough, and then you have to interpret it suitably.
Just a general remark that quantum mechanics does not mean that the wave function of every single particle is completely delocalized or entire volume. In fact, you have localizations within that volume. So what he may be meaning is that there is a distribution of the localization which is different with each event, right?
Each event has a different.
Yeah, has all different localization of particles. Quantum does not mean that all particles are localized everywhere. Even in an atom, we have electrons which are in different orbitals. They are localized. They localized in that region. They have a spread, but it is still within that. Wave function is vanishing outside this hall, right? Your electron is not localized outside this hall. It is within the cell or carbon molecule. Same thing holds true for the.
But radius of radius of orbit is not well defined in the hydrogen atom.
No, nobody is saying it's well defined, but I am saying that there is still localization.
But this is
It's not that it is uniformly probable everywhere. There is localization.
interact with them, with it, then
We discuss this over localization.
Okay, I will stop here. The rest of the talks I think will be on the blackboard. But I will still need to show some figures. So this the data has to be shown.